Okay, let's quickly discuss electromagnetic spectrum. And electromagnetic spectrum is a collection of different electromagnetic waves, okay, which are actually characterized or differentiated based on wavelengths, energy, and frequency. And of course, electromagnetic spectrum, the electromagnetic waves ranges from radio waves to gamma rays. All right, it ranges from radio waves to gamma rays. Radio waves, as it is itself, is has the longest wavelength. Okay, it has the longest wavelength and lowest energy, and lowest energy means lowest frequency. Okay, that means once it has lowest energy, it means it has lowest frequency. So radio wave is the one that has the longest wavelength and has the lowest frequency. Gamma rays, on the other side, has the shortest wavelength but the highest energy and the highest frequency. Based on their wavelength, based on their energy, based on their frequency is what is exactly the way they are arranged in the electromagnetic spectrum. Each of them is called an electromagnetic waves. So like you can see here, this is, if you look at the diagram that I'm showing on the screen right now, you see that this one here is the radio wave. Okay, you can see this is the radio wave here, and after the radio wave is infrared. You can see the infrared here. This is infrared. And after the infrared, you will see this thin line that is in between here. That is actually showing us the region of visible light, because after the infrared, it is the visible light. Okay, this is actually showing us the region of the visible light. And next to the visible light is ultraviolet. This is the ultraviolet. All right, this space here is actually for the ultraviolet, and beyond this is what the next is what X-rays, and you will see that the last one there is gamma rays. You can see this ultraviolet light here, this visible light that is here. You can see that is what is being brought out as this diagram that you are seeing. Okay, this colorful diagram you're seeing here, this colorful rectangular diagram that you're seeing here, is actually showing us the space that is between the ultraviolet light and the infrared. It's just like magnifying it. That is what you are actually seeing here. So which actually shows us that the visible light ranges from 400 nanometer to 700 nanometer. That's the visible light. You know that it ranges from 400 nanometer to 700 nanometer. And in the whole of this radio waves has the highest wavelength. That's the longest wavelength. That's what radio waves has the whole longest wavelength, but it has the lowest frequency and the lowest energy, you know. But on the other side, so if this has the lowest frequency and the lowest energy, so it means that the gamma rays on the other side, all right, the gamma rays on the other side has the longest, has the shortest, yes, the shortest wavelength, okay, and has the highest energy level and the highest frequency. All right, so so if you go on, the next diagram actually is a bit more practical, okay, about it. It's still the same diagram that is there, that is being presented in another format here. All right, so it doesn't matter where it is written, you just need to understand. In some diagrams that you will come across, you see the radio wave starting from the left, and in some diagrams that you come across, you see the radio wave starting from the right. You understand? But by the time you check the frequency, you will see that it is still the same, representing the increasing. It's either increasing from left to right, depending on whether the radio wave is on the left or right, or is increasing from right to left, depending on where the radio waves and the gamma rays are, and they are arranged accordingly. So which means that when you have, if we use the first diagram that we're having here, so if we have radio wave, next is infrared, and then you have ultraviolet, you have x-ray, and then you have the gamma ray, like that. So then now here we want to discuss the UV. Like I showed you the other time, here I showed you that this particular portion here is the visible light, right? Now let's see, and the other portion as well, which is here before the visible light, is the UV, that is the ultraviolet radiations. That's where it's actually occupied on the electromagnetic spectrum. So let's now see what the UV here says. So now we were looking at the UV region. Okay, you can see that the UV here is before the visible light, after the UV is the visible light, and then after the visible light is the infrared. Okay, so here you can see that the UV, looking at this, what you're having here, you can see 100 here and you can see 400 here. So which means that UV actually ranges from 100 nanometer to 400 nanometer, while the visible light starts from 400 to 700, and then infrared has 700 and above. You understand? So now what can we say about the UV region? Of course, it lies between the X-rays, okay, because before the UV here is the X-ray, is when you are coming from the left, when you leave the X-ray, the next is UV. Okay, so you have the X-ray, so it lies between the X-rays and the visible light in the spectrum. Okay, so it spans wavelengths of 100 nanometer to about 400 nanometer, just as we can see there. And now one key important thing here is that there are 3 different kinds of UV. Yes, 3 different. So the region, based on their region, the regions are divided into 3 basically. You have UVA, you have UVB, ultraviolet A, ultraviolet B, and ultraviolet C. Okay, ultraviolet C is the region from 100 nanometer to 280 nanometer. Yes, that's ultraviolet C, or that's UVC. Okay, and which is highly energetic and mostly absorbed by the ozone layer. Okay, ozone layer actually absorbs it, so it's really doesn't reach us, here on Earth, because the ozone layer would have actually absorbed it. Then you also have the ultraviolet B, that's UVB. Okay, which is between 280 to 315 nanometer. Okay, 280 to 315 nanometer. Okay, this causes DNA damage. Okay, so this is the one that causes DNA damaged. Okay, and then you also have ultraviolet A, which is 315 to 400 nanometer. Okay, penetrate deep into skin. Okay, and used in ultraviolet lamp. Okay, and then now let's quickly discuss the visible regions. Okay, the visible regions, you see, both the visible regions and the ultraviolet regions are very important to. Okay, so that's what we have. So that particular region is what is brought out here for us to see. That same visible region that we actually brought out the other time is what, and in here you have the red, you have the orange, you have the yellow, all right, you have the green, you have the cyan, you have the blue, you have the violet. All right, so all these are within the visible region that you have. And then now, so here I have a table summarizing what the content of the electromagnetic spectrum basically has, what it actually contains, what is made up of. Okay, so here we are having the types of radiations, you're having their wavelength, you're having their energy. Okay, the level of energy that is actually within that particular this thing, and then the examples of uses and what they are used for. Okay, so in questions I might just ask you to I might just ask, you understand, so you might just be asked to actually state the components of electromagnetic spectrum, okay, and their characteristics. okay, or maybe their characteristics which talks about their wavelength. Wavelength, frequency, whatever, but wavelength basically, in most cases wavelength. So you can have energy, you can also have examples as well. So you have, so the first one, you have the gamma ray, which is less than 0.01 nanometer, and the energy level is very high, just like we said earlier. And then you have the example, that's the uses, okay. It's used for cancer treatment. And you have the X-rays, okay, the X-ray, which is between 0.01 to 10 nanometer high, which the energy level is high too, okay. Medical imaging, like in X-rays and all that in the hospitals, okay. So you use that. Then you have the UV, which is between the 10 and 400. No, that's not the case. Is between 100 and 400. Yes, it's between 100 and 400, sorry. So you have, and that's medium high, okay, which is used in sterilization, fluorescence, okay. And then the visible light, which is about 400 to 700 nanometer, okay, which is medium, optical microscopy, okay. That's the uses. And then you also have infrared, which is high half, okay, which is from 700 nanometer to 1 okay, then which is low in energy, okay, thermal imaging. And then you also have microwaves, 1 to 1 okay, which is very low. All right, so cooking radar, so you can use it for cooking, you can use it for radar. So the way question might come under this table might actually be presented to you, all right, and you will find in some lines, like the first one, now you can have gamma rays left being there, you have the wavelength missing, you have the energy level maybe missing, and then you have maybe uses left there, so you have to fill up the missing spaces. All right, so questions can come in that form. I'm not saying it's going to come in that form, but it can actually come in that form. That's what I'm trying to make you see reasons. So you can have, I can go to visible light now and then eliminate 400 to 700 and eliminate the uses on the other side, which is optical microscopy, and then I expect you to fill in the gaps. All right, so I might just look like one of them, 1 2 3 4 5, maybe I might just pick like 5 of them and decide to just let the missing space, there be missing spaces here and there, and then you will fill up. So that might be a form of question for you. So okay, now let's look at what we mean by UV and visible radiation absorption. Like I told you that the UV and visible radiation, as far as the electromagnetic spectrum is concerned, is one area that we are interested in. All right, so we know that molecules absorb UV and visible light, okay. The UV and the visible light, you know, they are side by side, you know, they're very close. So the UV absorbs the UV, so molecules of compounds, okay, absorb the UV and the visible light, okay, causing electronic transitions, okay. Electrons move from a lower energy level to a higher energy level when they absorb. Just like in this diagram that you can see, what we are basically saying there now is in this A high diagram that I generated here, that you can see here. So you have here, you can see the light, all right, which is the source of the energy that is coming in, okay. So now eating this molecule is air, all right, this molecule. So eating the molecule, all right, which are at a resting state or a ground state, all right. So what happened is that once the UV, that's what this is representing. This is representing UV or visible light. So once the light shines upon these molecules, that means energy is being transferred, and then they will gain more energy. And when they gain more energy, definitely they will want to move. And moving now meaning that they leave this particular energy level, okay, and move to a higher energy level. And that is why in this diagram, that is why you can see some of them flying. Those are the ones that have actually gained enough energy for them to move from the lower energy level to a higher energy level when they absorb either the UV or the visible light So either they absorb the UV or the visible light. So electrons will actually go from the lower energy level to a higher energy level, and that is what we refer to as transition. Okay, when an electron goes from, in a molecule, when an electron goes from the lower energy level to a higher energy level, that is what is known as transitions. And because these ones have actually gained energy, you understand, from the light, then they are able to leave that particular energy level and go to the next energy level. And this is what happened. There are 4 types of bonds that are present here. Look at the diagram that you're seeing here. So there are 4 types of bonds that are present. The 4 types of, when they are going from lower level to higher level, there are 4 types of transitions that are possible in molecules, all right, under this electromagnetic spectrum thing. So there are 4 types of bonds that are the 4 types of transitions that can occur. Okay, like you can see here, you can see a sigma to pi star bond. Okay, you can see a sigma to pi star bond. Now look at the first part of the diagram. It's showing us the various levels, the various electrons that are present. Okay, so you can have a sigma electrons, okay, a sigma electrons, of course, which is from a sigma bond, okay, and then you have a pi, you have what is known as a non-bonding, which is N here, non-bonding, all right, non-bonding electrons, and then you can also have the pi star, and the pi star and the sigma star are referred to as the sigma star is referred to as the anti-bonding. Okay, then you also have the pi star. The pi star is also known as the anti-bonding pi star bond, anti-bonding pi star. All right, so you have that particular electrons, okay, there. Now what happens is that electrons can go from this level to higher level, okay, but when it is going from this, when it's this pi electron, when it's sigma electron here, all right, which is going from the bonding electron, okay, which is the sigma here that you're having here, then it's going to the sigma anti-bonding. You can see, so from this to this is one type of bond, which is from sigma to sigma star, is one type of transition. You can also see another transition here, which is going from sigma, all right, from sigma to this non-bond, to pi star. Okay, is going from sigma to pi star. Okay, that's another kind of transition. All right, and then you also have this as well, the third type of transition, which is pi to pi star. Okay, yeah, that's the second one. Then the third one, you can have it from the